Hello Science Alliance, hello my IGCSEs. It's lesson 3 of energy. We've done forces, we've done electricity, we've done waves, and we're on energy lesson 3. We need to do a little bit of forces revision actually before we get on to anything else. So, because some of you might not have seen forces, and if you have, this will still be good revision. So we're going to talk quite a lot about weight today. Do you remember the difference between weight and mass? Weight and mass. Mass and weight. So mass is measured in kilograms, and you could say it's how much stuff is in your body, or you could say it's a measure of how difficult it is to move a thing. But whether you're on Earth or on the Moon or on Jupiter, don't go there, but your mass is always the same, okay? So obviously the amount of stuff your body is made of doesn't change if you're on Earth or on the Moon. It's weird, but if you got hit by an elephant as you were both floating through space, it would be just as hard to stop. It would be still hard to stop the elephant because it is more massive. A little mouse doing the same thing would be less hard to stop. The mouse is less massive. Right, hopefully that's not just confused you more. So mass, let's just say it's how much stuff is in your body, and it's measured in kilograms. Your weight, or weight, is a measure of how much mass is getting pulled down, say, towards a planet or a body of stuff. So if this is Earth, how much Earth is pulling on masses is it pulls with a force of 10 newtons for every kilogram, right? So a 1 kilogram mass hanging around in space is getting pulled on by a force of 10 newtons, okay? A 2 kilogram mass, well, the Earth pulls on it with a force of 10 newtons for every kilogram. So a 2 kilogram mass would get pulled on with a force of 10 newtons, all right? So this is like called the gravitation. Oh, I've written it. Wait, this is so confusing. Sorry, I've written that backwards, haven't I? It's because I've just been doing a Facebook lesson where I have to write backwards. There. As if IGCSE physics wasn't hard enough. Right, yeah. So weight is how much you're being pulled, the force with which you're being pulled down to Earth. And weight is different on the Moon because the Moon's got a different gravitational field strength. Jupiter's got a different gravitational field strength. So you could be pulled on with a force of like 20 newtons per kilogram. So, or 13 newtons per kilogram, just depends. For today's lesson, I am just going to be talking about weight. So I'm going to, just tell you that a thing weighs like 4 newtons. Weight is a force. It's how much it's being pulled to Earth. In the actual exam, you'll quite often get asked about something in kilograms, and you'll have to convert it into weight. There's just like a word of warning that we're talking about weight, which is a little bit like mass, but it's how much mass gets pulled out. It's measured in newtons because it's a force, a push or a pull, right? Okay, so we can actually start the lesson now. We've been talking about energy and how energy gets transferred. So I have written here, heat is when energy is transferred because of a temperature difference. We have looked a bit at spoons. So my body is a certain temperature. This spoon is colder. So if I hold this spoon, then heat is transferred to the spoon. Yeah, we've looked at this. Body, hot, spoon, not hot, temperature difference, heat is transferred. So heat is just energy being transferred because of a temperature difference. If this spoon was exactly my body temperature, energy would not flow from my body to the spoon because there would be no temperature difference. But anyway, we're not talking about heat today. We're kind of talking about the opposite of heat. So heat is when energy is transferred because of a temperature difference. What do we call energy transfers that don't happen because of a temperature difference? Was the point of the lesson. We call it work. So if energy is transferred and that's not because of a temperature difference, then we call it work. So you could say work is done when energy is transferred mechanically by a force. So if I take my little wormy here and I lift her up, there's no temperature difference going on, but as we've looked at, I am shifting energy from my chemical store in my body to Wormy, because Wormy's high up in the air, so she's got more gravitational potential energy. So energy is being transferred from me to Wormy. There's no temperature difference. This is work. And in fact, there is a force happening, right? I am pushing her up. Moving on. So we say that forces do work to transfer energy. Just get used to the language, because obviously the word work doesn't mean the same in physics as it means in everyday life. If you push a box along the ground, you are doing work because you're using a force to transfer energy. If a force is being used to transfer energy, then you're doing work. So here you go, you're pushing this box, say, with a force of 4 newtons. So you are doing work. This crane, let's just put it, I've done so much talking, let's put it back on you for a bit. This crane is doing work. Are you okay with that? It is moving something, shifting energy from itself to this metal bar, using a force, so it is doing work. It's transferring energy from its something store to the metal bar's something store. How many lessons have we done? 2 lessons on energy. I think you should be all right with this. The crane is shifting energy from its chemical store. Could be running on petrol or diesel or electricity, but it's still some sort of chemical reaction probably happening to shift energy from the chemical store to the metal bar's gravitational store, gravitational potential energy store. Well done if you got that. Electric work is a thing too. I'm not really going to talk about it today, but electrical work, a current flowing, does work, we would say, against, say, the resistance of a wire. So that is a force as well. Right, get a baking tray and a piece of Tupperware. We're going to do possibly the least exciting activity we've done so far. There was science anyway, but anyway, it's important for learning. Yeah, I'll just flip you. What I'd like you to do is just get a piece of Tupperware, put it on a table, and then put a baking tray on top of it so that you've got a slope like this. Oops, sorry, terrible. You ready? Tupperware, baking tray, slopiness. And what I would like you to do is get some sort of Lego brick, she says, frantically looking around. Where's my Lego brick? Oh, well, doesn't matter. It could be anything. I'll use this box. Get a Lego brick or something, put it at the end of the slope, and just push it up to the top of the slope. Are you happy that you are doing work in this situation? So energy is being transferred from your chemical store. You're shifting it to the box's kinetic store. And you're also probably slightly warming up the tray because friction. So you're filling the tray's thermal, shifting energy to the tray's thermal store, you could say. And then the box gets to the top, and you've shifted energy from your chemical store to the box's gravitational potential energy store. Is that all right? Okay, so you've done some work. You've transferred energy, and it's not because of a temperature change, it's because of temperature differences, because of you applying a force, right? Think about how hard that is to do. How much energy you think your body is shifting. Then put the baking tray on the table and put the Tupperware on top this time. So you've got more of a step situation, and lift the thing onto the Tupperware like that. Which one of those ways, going up a ramp or just stepping, which one of those ways do you think you're doing more work? Which one is shifting more energy? Remember, work is just kind of the amount of energy that is transferred, you could say. Work is a measure of how much energy is transferred when a force is applied. What's harder, that? Basically what I'm asking is, isn't it, does it burn more energy to walk up a ramp or take the stairs? So you could think the answer to this question will actually be quite interesting and useful in everyday life. Flip you around. Whether you want to conserve energy or burn energy could make a difference. I'm not actually going to tell you the answer yet. We need to look at the equation, but what do you think about that? Which one do you think is harder? Which one shifts more energy? We need to look at the equation for work now. Yeah, equations, we love them. Oh, they make life so much simpler. So here's the equation for work. It's pretty straightforward, isn't it? The equation for work done is force times distance moved in the direction of the force. All right, you little pros. It doesn't matter if this question completely freaks you out. You will just learn something if it does. But some of you might be thinking, what is the unit for work or work done? Same thing. What's the unit for work done? We have talked about this before, but not in this module. So this is your first module. You won't maybe have a clue. If work is force times distance moved in the direction of the force, what's the unit for work done? Like the unit for speed is meters per second, yeah? The unit for distance is the meter. If you were calculating work done, you could say it's 10, what's the unit? So I'm hoping that some of you will know that when you want to find a unit, you just do the same thing to the units as were done to the numbers. So for example, if you want to work out like 3 times 2, then you do the 3, obviously, times the 2, which is 6. But if it's like 3 newtons times 2 meters, then to work that out, to work out what the answer, the unit is, you just do the same things to the units as you've done to the numbers. So a newton times a meter is a newton meter. Be careful, if it was newtons divided by meters, then the unit would end up being like newtons per meter, but it's not. Just confusing things, Lara. So the answer, you might well have said, is the Newton meter. And indeed, you would not be wrong. It just so happens, though, that the Newton meter is another name for another unit as well, which, yes, you absolutely no reason why you would have known this. But yeah, if you're doing a force, which is measured in newtons, times the distance, which is measured in meters, then the answer is the Newton meter, but it just happens to be the joule as well. So like I say, work done is a measure of energy. It's how much energy is being transferred or shifted when a force is applied. But if you write your answer in Newton meters, I think that's probably quite a good idea, because then you know you've done all the calculations correct, and then you can just change it into joules at the end, because joules is sort of more, it's just a nicer, more correct way of saying it, but Newton meters isn't wrong. Right, so this point about the distance is in the direction of the force, I just want to talk about that a little bit before I give you some questions to do, okay? So this crane, we would say it's doing work against gravity. The direction of the force is against gravity. Gravity always acts down. Always, nowhere on the planet where gravity isn't just being isn't acting exactly downwards. So the direction of the crane's force is working against gravity. Are you okay with that? It's working in the opposite direction. If you're pushing a box, yeah, you would say that you're doing work against friction. So you're pushing in that direction, and the friction is pushing in the opposite direction. Are you doing work against gravity? If you're pushing, people are always pushing boxes along surfaces in physics, I don't know why. Are you doing work against gravity if you push in a box against a ground? Are you doing work against gravity? I know this is a good question because on Facebook it was one of those ones that made everyone like fall out and say different things. The answer is, have you said something? I hope you've said something. Are you doing work against gravity? No, you are not, because work done is force times distance moved in the direction of the force, and there's no force acting against gravity in this situation. Gravity acting downwards. There's no work being done against gravity because there's no force acting against gravity. The force is in the sideways position, right? So now I think you're ready for these questions. Here we go. Off a 4-meter high shelf. How much work is done by gravity this time? Not against gravity, but by gravity. A crane lifts 8,000 newtons onto a 20-meter high scaffold. How much work does it do against gravity? So reminder, work done, or work, is force times the distance moved in the direction of the force. A T-Rex drags a 40,000 newton Triceratops 100 meters to its nest. How much work does it do? Raphael, couldn't use a picture of the turtles for copyright reasons, love them. Raphael lifts a 300 newton weight and shifts 300 joules of energy from his chemical store. How high does he lift the weight? An acrobat weighing 900 newtons sits on a hoop and is lifted 18 meters into the air. How much work does she do? A box weighs 5 newtons. A woman pushes it with a force of 4 newtons. It travels for 2 meters. How much work is done against gravity? Phew. And if you did forces with me, the very first module that we did, is distance moved in the direction of a force a scalar or a vector? Ooh, can you remember what a scalar or a vector is? Good practice, isn't it? We should do that more, referencing previous modules, really. That's a revision. Some of them might be evil trick questions, by the way. Sorry, just to drop that in. Some of them might be, and I'll say now, they might be. They are. I'll give you, I don't know, 40 more seconds. That's teacher seconds, so I'm not counting. Just feeling. If you're totally done, you can always like and subscribe, can't you? Or go over to my Facebook page. On my Facebook page right now is a little post saying, if you're watching live on YouTube, please say hello here. Okay, should we go through the answers, and then the people who are really unsure, they can obviously learn from the answers. So, a cat weighing 20 newtons falls off a 4 metre high shelf. How much work is done by gravity? Well, just check it's not a trick question. How much work is done by gravity? Gravity is acting downwards. This cat is being pulled downwards, so yeah, it seems fine. So you just plug in the numbers. So this is the worm, by the way, my beautiful wormy topper that Joe made me. You just do the force, which is 20 newtons, times the distance moved in the direction of the force, which is 4 meters. So the answer was 80 Newton meters. I'm going to write it like that, and then I'm going to say, but I know that Newton meters is also means joules. This crane lifts 8,000 newtons onto a 20 metre high scaffold. How much work does it do against gravity? Again, it's lifting upwards and gravity is acting downwards, so that is against gravity. It's not a trick question. And I don't know, I'm a physics teacher, not a maths teacher, so I would do 8 times 2 and then add all of the zeros. So 8 times 2 is 16, and then you've got to add 4 zeros on. So it's 160,000 Newton meters, which is 160,000 joules. If you're panicking and I'm going too fast, obviously this is going to be on YouTube as soon as I've finished. A T-Rex, this is true, lived alongside Triceratops, would have eaten them, probably only smaller ones. A T-Rex drags a 40,000 Newton Triceratops 100 metres to its nest. How much work does it do? Is that a trick question? Well, it's applying a force and it's moving a thing a distance, so no, that's not a trick question. So it's 40,000 newtons times 100 metres, which is 4 times 1, and then add 6 zeros, which gives us 4 million Newton meters, or 4 million joules. But that's a bit silly. So I would probably think, okay, I'll take 3 of those zeros away, divide it all by 1,000, and instead of saying joules, I'll say kilojoules. So you can take 3 of those zeros away and replace it with kilojoules. And even that, you could take another 3 of those zeros away, so you've divided it by 1,000,000, and instead of joules, you could say megajoules. So it might say, give the answer in megajoules. You might get a mark for that, you never know. Raphael lists, well, you have to do a little bit of rearranging here. This time you've got the weight and you've got how much energy was shifted, but how high does he lift the weight? Well, I don't know, you could turn it into a triangle if you like that kind of thing. You could pretend that work done is on top of force and distance. So you end up with distance is equal to work done, or energy shifted, divided by force, which is 300 joules divided by 300 newtons, which is 1 metre. I mean, I had to make it 1 metre really, didn't I? It wasn't going to be 2 metres. They're only, like, I know they're mutants, but they're not bendy. Anyway. Right, this one, these were both trick questions. I'm really sorry. Did you get that? These are both trick questions. If an acrobat is sitting on a hoop, in fact, I'll bring you up here. If an acrobat sits on a hoop, she just sits there and she gets pulled into the air. She's not actually doing any work because she's not applying a force, and she's not. It's not the result of her force that is moving anything. So she's not doing any work. If there's a person stood next to her, like pulling on a rope to get her into the air, they would be applying a force. They would be pulling, and they would be moving a distance and shifting energy, like from their chemical store to the gravitational pull energy of the acrobat. So they would be doing a lot of work, or a machine, you could say, could also be transferring energy from its chemical store to the gravitational potential energy store of the acrobat. So the machine will be doing work, but the actual acrobat in this situation is no different to like the metal bar attached to the crane. So she's not doing any physics work at all. I'm sure she's doing a lot of work in circus terms. And the box, did you get this? This was what we were talking about before. She's pushing it, and I've given you all the numbers, but it's sort of a trick question because she's not doing any work against gravity, because she's not doing any forces that point upwards. You can, if she was like pushing diagonally, then you've got to do the resolving vectors that we covered in one of the forces lessons. So if you push diagonally, do you remember, that means like there's a component of your force acting that way across, and there's also a component of your force acting upwards. So going diagonally, she would be doing some work against gravity, but it wouldn't be equal to you wouldn't be able to use the number that was the push of her force. You'd have to work out the vectors, but that's another question for another day when we do revision. And if you did forces, talking of forces, is distance moved in the direction of the force a scalar or a vector? Do you remember a scalar is something that can be described with just a number and a unit? So 5 meters, that's a number and a unit, so that's a scalar. 10 joules, that's a number and a unit, so that's a scalar. A vector is the same, but it also has a direction. So like 10 meters per second to the left, that's velocity, that is a vector. Distance moved in the direction of the force, that is a vector because it's always got a direction applied to it, right? It's distance, but in a certain direction. So yes, it is a vector. Work done, measured in joules, that's a scalar. 5 joules, perfectly good answer. If you're talking about distance moved in the direction of the force, you can't just say 5 meters really, you've got to draw an arrow or something, haven't you? Say which direction. Oh, so yeah, I've put, it's actually displacement. Sometimes it's described as displacement. Okay, just 2 tricksy little questions to see how much you've understood, and then we'll finish. I don't know whether to be a smug teacher about this and be like, yeah, I've caught you out, or think, have I caught you out? I don't think I've made a mistake. I think I can be 100% smug teacher about this. These people, so this comes back to our exciting Tupperware baking tray activity earlier. These people have got this box, which weighs 4 newtons, to the top of the hill. All right, same box, weighs the same amount, the hills are the same height, it's just like our activity. They've got this box weighing 4 newtons to the top of the hill. One of them has gone up a slope, which is 5 meters long. The other one has taken the stairs, which are 0.5 meters wide and 0.5 meters tall. But they've both reached a height of 3 meters. How much work has each one of these people done against gravity? How much work has each one of these people done against gravity? I'll give you 30 seconds. I am actually counting 30 in my head. That's very unusual for me. I'm counting at gig speed, actually. If you've ever been in a band, you heard of gig speed? It's where the whole band's like really nervous and excited about playing the gig, so they play all the songs much faster. So whenever you practice in a band, you're like, well, our set is an hour long, but it'll be 40 minutes long at gig speed. So apologies if I'm going a bit fast. The answer is They've done the same amount of work against gravity. Gravity acts downwards, so we're only looking for how much work they've done against gravity in the upwards direction. So you're only using the distance in the direction of the force, which is the 3 meters in both cases. So you do 4 newtons, because that's the weight, times 3 meters, which is 12 Newton meters, which, as we know, is 12 joules. They've both done the same amount of work. And this is, a physicist would say that taking the ramp or taking the stairs shifts the same amount of energy. In biology, it's a bit more complicated because of like the muscles in your knees and how much they work. But yes, a physicist would say you had shifted the same amount of energy whether you walk up a 3 meter ramp or whether you take the stairs for 3 meters, because it's the height difference that you're looking for. All right, final question. Here we go. You've got 2 identical boxes here. They weigh the same. They're moved onto a table. The arrows show the movements the people did to get them there. So you've got box A, where the person's just picked it up off the ground and put it on the table. And you've got box B, where the person's picked it off the ground, done some kind of cool twirly dance, and then put it down onto the table. Question 1 is, this is the last thing we'll do. Which person did more work against gravity? Person A or person B? Or did they both do the same amount of work? And which box has more gravitational potential energy? Which person has done more work against gravity, A or B, or did they both do the same amount of work? And question 2, which box now, at the end, now they're both on the table, has more gravitational potential energy? Water, but my water tastes like 5 Spice because I used my tornado jar from the lesson earlier today. How are you getting on? I don't think I wrote the answers on the sheet. Let's see. Oh yeah, I did. Person B did more work against gravity because they moved higher, so they went a further distance in the direction of the force. The distance in the direction of the force, right, is how much distance they pushed against gravity. So actually this person did do more work because they went higher up. But in the end, both boxes have now got the same amount of gravitational potential energy because they're both the same height above the ground. This is a good question, right? Come on, it's a bit confusing. But how do you work that out? Because work is supposed to be a measure of how much energy was shifted, isn't it? Work is measured in joules, it's how much energy is shifted by a force. So how come, if they've both now storing the same amount of energy, how come person B, how can they've shifted more energy? Well, it's because not all the energy that they shifted is being stored in the box, is it? Because they did this cool twirly dance. So some of the chemical energy from their body has been shifted to like heating up the air and kinetic energy of their arms. So yeah, basically, eventually some energy would have been wasted like in the air because they did their awesome dance. This one is more efficient. So this person shifted more energy, but yeah, this person warmed the air up more. Whew. All right, that is, yeah, I was saying yesterday, every time I'm planning these lessons, I'm like, oh, this one will just be a nice straightforward one. And then I get to the end of it and I'm like, oh, that felt like a lot. Okay, I'm gonna go over to my Facebook page and say hello to anyone who has visited my Facebook page and left me a little message. But if you're watching on catch up, you probably don't want to watch this bit. It might be a bit boring for you. Thank you so much for watching on catch up. I really appreciate it. If no one was watching on catch up, then there would literally be no point me doing these lessons really. I mean, it's nice that these 19 people are live. Like, I would probably do it for them, but they might come to the Facebook one, you know, if you like live. So, but I do really like hearing from people who've watched a lesson from like a year ago on my page. But like I always say, also very grateful to the people who are watching live right now, because if you weren't watching live, I would have no motivation to do this lesson. I would have a cup of tea and think, oh, I'll just teach it later. And then I never would, ever. And I wouldn't have a job. Right. Yay, comments. Who's here? No way, Stephanie said for the first time. Man alive, I hope you're okay. I hope you're right. I hope you're still here. That was quite a lot for the first one. The all ages lesson. Oh, Henry! I did not catch Henry out. Are you kidding? That is impressive. Oh, Sky and Evie are here. Hello. Oh, that's great. Oh, I didn't know you were coming. John and Seamus, hello. Can't get enough of you. Let's see what we do. Oh, hello, Shyla. It's your 14th birthday tomorrow. Dude. Shayla, that is awesome. 14. That's big. I'm a little bit intimidated, to be honest. Now you're 14. I'm a bit like... Hello, Eleanor. Oh, thanks, Kyle. That's nice. Wow, 14. Have an amazing day. Oh, that's a good one, isn't it? Eleanor's here. Yep, that's fantastic. Sky and Evie here. Henry, not been caught out. Stephanie, I hope you're here. The all ages lessons, I sort of pride myself on. You should be able to jump in at any time. We just can't really do that with the IGCSE. I mean, you can. I just worry that you get really freaked out because it'll seem really hard, even though it's not hard so much as it's just we've covered a lot of stuff that you don't know about. But hopefully you found that okay. Right. Yeah, I'm going to go. Going to go do the school run and plan next week's lesson. We are going to do kinetic energy and gravitational potential energy and look at the equations and how you do the sums. Because talking about energy without numbers is a bit like trying to teach about money without saying any numbers. It doesn't really make sense. If you want to support me, you totally can. You can pay me. I'm sure most of you know this by now. You can go to my About section on YouTube. It takes you to this website called Coffee and you pay me £5 a month and I send you nice things to say thank you ever so much. It is really very much appreciated. It's good to sign up for IGCSE, isn't it? Because you get rainbow glasses, which are actually diffraction glasses, which might help you understand waves, especially because I send you an information sheet as well. So I've just knocked Wormy out of the... Hello, Kyle! I was just refreshing my comments because I heard that you had put something else up. There you go, Wormy. Sorry, little lass. Right, I'm going to go... I always say that. I'm still here. Oh! Good. Yeah, that's calm. Okay, right. See you soon, everyone. Thanks so much for joining me. Bye!